All right. Hello, everyone. Let's get started. Welcome to the second session of LEOCONN webinar series. This is a webinar series on low Earth orbit or LEO satellite networks. And we plan to have a series of sessions with 2 to 3 tech talks per session on LEO network opportunities, challenges, measurement platforms, etc. And the broader idea here is to bring the industry and academia closer together and build a LEO consortium. So today we have two great speakers, two very interesting talks lined up. Our first speaker is Vaibhav Bhosale. He is a second-year Ph.D. student at Georgia Tech. His research is focused on building systems and networking solutions for LEO satellite networks. His main research agenda is to build software abstractions that can enable application developers and users to use this new frontier of computing seamlessly. He has explored different aspects related to LEO satellite networks, such as application deployment, route variability, and cellular deployment. He completed his undergraduate studies at the Indian Institute of Technology, Mumbai, and his master's at Georgia Tech, and has interned at Microsoft AfO, Mediatek, and IBM in the past. With that, I hand it over to you, Vaibhav.
Thank you for the introduction, Vaibhav. I'll just quickly share my screen. So, okay, I hope my screen is visible.
Yes.
Yeah, thank you. So, thank you for the introduction, Vaibhav. I'm glad to present my work on enabling the LEO satellite edge ecosystem today. And so I have been working on in this topic as part of my PhD studies at Georgia Tech, being advised by Professor Ada Gavrilovska and Dr. Ketan Bharadwaj. Now, I'm fairly certain that most of us in this room are aware about LEO satellites and the buzz surrounding them for the past few years. So I'll not get into the details here and quickly move on to the notion of LEO satellite edge. LEO satellite edge has been an attractive concept for researchers in industry and academia alike because of the benefits it can provide compared to the bent pipe architecture. Essentially, as part of a LEO satellite edge, you will deploy applications directly on the satellites so that the satellite can respond to user queries from the satellite itself without having to send the request all the way to the ground station and beyond. As you can imagine, this will help you achieve faster access latency, as well as save on the bandwidth, save on the ground station satellite bandwidth, because you do not end up using that side of the network at all. Previous work has shown the utility of a LEO edge for different types of high-value applications, such as content delivery networks, meetup servers, IoT applications, and so on. Looking at this, we were curious to explore what it would take to build an ecosystem where application providers can use these satellites as the new edge infrastructure. So when we started, there was no existing notion of a LEO edge or LEO edge ecosystem. So we looked at the terrestrial ecosystem as the starting point. A brief background here. So the way things work there is, if an application developer, you want to deploy your application into a specific region, say Atlanta, you will have to select from a list of regions available like this. This is in the US East. You select one of these regions, send this information over to an edge provider, which will identify the nodes as present in that specific region and deploy your application on that node. Now, the edge provider here is able to do so because it is aware about what nodes are physically present in Atlanta, and so it can directly go to those and deploy the application. So the first question we asked ourselves was, can we do something similar for a LEO edge? Unfortunately, since satellites are continuously moving, you cannot tie down a particular satellite to a region, and hence there exists no abstractions to deploy your application for a particular region. Well, you might say that, okay, that was a very trivial use case. Can you not do something a little smarter? That is, deploy your application on a satellite that is visible from Atlanta. Well, if you do that, the application will be accessible for a few seconds, for a few minutes, but then once the satellite moves out, the application becomes unavailable. You would have to redeploy your application on another satellite, which will again move out in a few minutes. Essentially, what happens here is that As soon as the satellite hosting the application moves out, the application becomes unavailable. So to counter this, we introduce the notion of LEO regions. What are LEO regions? So LEO region is a high-level abstraction that we defined to deploy to aid application providers to deploy their application. In this case, I'm showing the example of a circular region. As part of this, an application provider simply has to give the information related to the region as part of the application config or the YAML file. Here, as you can see, the application provider has to simply provide the center of the region as part of center of the region, that is its latitude, longitude information, and the radius of the region. And that's all it needs to do to get the same abstraction for a LEO satellite edge. Now, the way this works internally is that for every LEO region defined, the system will internally define a space projected region. The space projected region is the region formed of the region that can contain all the satellites that are accessible from the entire region. Because here we are trying to serve an application for the region, so that is why this distinction is important. And a key artifact of this turns out to be that if you keep increasing this size of the region, your space projected region shrinks. That is, if you want to serve a very large region, the number of satellites that can essentially do that keeps decreasing as you keep increasing the region. Now, as you would have seen, like this is a fairly open definition of how we are defining regions. We are giving the application provider a lot of control here. This is like we think about this as a good thing, that the application provider has fine granular access to define their own regions instead of having to choose from a list, as I'd shown as I'd shown a few slides ago. Essentially, the application provider can control what size of the region they want and where it needs to be and they have full freedom for that. As an example here, I show that instead of, for example, in this application that was designed to serve 2 different points in 2 different cities, instead of having to use 2 separate regions, because you're able to define your own region, you can serve that using a single region. So LEO regions, while they helped you provide an abstraction for application developers, you still need to do some more work to ensure continuous availability of your application. Now, as I had described earlier, as soon as the satellite hosting an application moves out, the application becomes unavailable. Well, a simple next point for this, direction to this could be you deploy your application on multiple satellites, so that whenever the first satellite moves out, the second satellite can come in and continue serving the same application. However, we observe that to be able to achieve no downtime with such a strategy, you would need to deploy the application on the entire orbital plane, which in our case, or which in the case of the first shell of Starlink, comes out to be 22 instances. So essentially, to get continuous availability, you would need to run the same instance of the application on 22 different satellites. And an interesting point to note here is that over time, as the orbital plane keeps moving away from the region, you would start seeing some downtime then as well. So essentially, the key takeaway here is that simply increasing the number of application instances does not guarantee availability for your application. So to solve this, we looked at one other strategy that has been discussed in some of the recent work, that is performing handovers. Now, while application handovers is an attractive idea, most of the current terrestrial systems are incapable of doing that. For example, in this case, we looked at Kubernetes and the amount of time it takes to successfully migrate an application from a node that became unreachable to another reachable node. We observe that it can take about 5 to 6 minutes to successfully migrate the application, which adds in a lot of latency in the critical path and can keep adding this downtime repeatedly. Therefore, we decided to leverage path prediction models, which help us determine the position of satellites to enable to perform application handovers. The way this works is that, for example, at a given point in time, you have a workload instance running on the satellite node. When that node is about to move out, the system will deploy a new instance of the same application on another satellite that is either present or about to move in. Only once the new instance is completely initialized will the older instance be killed. This is to ensure that you don't see any downtime because of this. So that you are able to hide the downtime during the application handover process. Now you might think that, okay, I performed this handover and we are good to go. But I'll tell you that there are some kind of handovers that you can call them as bad handovers, which is because some satellites which is because from a particular region, you can have sometimes more than 30 satellites visible, and some of those satellites are visible only for a few seconds. So if you end up making a bad choice for a handover, you could end up performing a handover every few seconds. Therefore, as part of our system, we were able to optimize the handovers to ensure that the satellite chosen for the application handover would remain accessible for the longest duration of time, essentially reducing the number of handovers that would take, essentially reducing the number of handovers. In this graph, we compared our strategy on the right with two different strategies. The first one was basically you migrate your application to a random satellite node compared to the one that I just described. In this case, you can see that the average time between handovers, it's almost twice that we observe for our strategy compared to the random node. Essentially, this reduces the frequency of handovers by half. So, so now, like I talked about two different design abstractions that we built for this. So let's see where we are with respect to the original problem that I had stated. Earlier in my presentation, I had showed you this figure, which is how application developers are able to deploy their applications in a terrestrial edge. So the way this will work as part of our system is, if an application developer wants to deploy their application for a target region, they'll submit this request to our system called as Krios. This system will send this application deployment information to a ground station that is closer to the region. This ground station will deploy this application onto a satellite that is accessible from the end user, and the same ground station will continuously monitor the application to perform periodic handovers to ensure continuous availability. Now, how does this ground station do that? The ground station will run a thin layer a thin software layer consisting of 4 components, which is what we define as the Krios system. So the Krios system is designed to operate at a layer above the current orchestration stacks, which enables it to inherit the rich feature set of orchestration stacks such as elastic scalability, fault tolerance, and so on. First, I'll describe the two main components, that is the Krios scheduler, which is responsible for scheduling the application when the application is requested by the developer to a visible satellite. And the Krios rescheduler, as the name suggests, would continuously monitor the application and perform necessary handovers periodically to ensure continuous availability. Both these components use the orchestrator interface we created to interact with the underlying orchestration stack, that is Kubernetes in our case, and use the path model interface to interact with the path model chosen in our case. The reason for such a component design is to have Krios extensible enough to be able to operate with any underlying orchestration stack or any path model to be used. So let's see how does this system compare with some of the other orchestration stacks that exist today. First, I'll briefly describe the setup and methodology that we used. So for these experiments, the primary metric that we looked at was worst case latency, essentially the largest latency that a client in a specified region can face over the 100 minutes of our experiment duration. We compared Krios with a basic version of Kubernetes, and some augmented variations that I'll describe later. We looked at the first shell of Starlink consisting of 1584 satellites made available as part of the FCC filings. And we set the latency for a ground station satellite link as 9 milliseconds, as that was the lowest number we observed. That was the lowest latency we observed on Reddit. So moving on, first I'll show you the results on application performance that we observed. We looked at two different applications. First one being Internet of Things server, wherein the client periodically sends small heartbeat messages to the server and the server just responds with a 204 accept. And second is a content delivery network where the client periodically sends in GET requests and the server responds back with a large large size response. And I will compare multiple baselines here, starting with basic Kubernetes, where a single instance of the application is running in the entire constellation. Then we look at 2 instances running, 4 instances running, 11, 22, essentially covering the entire plane with 22. And like a point to note about these is, like, in this case, when multiple instances are running, they are all running on the orbital plane closest to the region. Next, we also look at federated Kubernetes. The notion of a federated Kubernetes here means that the only satellites considered for application deployment are the ones that are visible from the ground station. And finally, we compare all of their performances with Krios. So firstly, for IoT application, we can see that only the strategy of deploying the application on the entire plane can give you latency comparable to Krios. In all the other cases, you suffer heavily on the tail latency, even with multiple instances. Or whereas in some cases, when you have fewer instances available, you suffer even at the median. Similarly, for a CDN, we have similar findings that most of the cases suffer with a high tail latency, but if you run fewer applications, fewer instances, you suffer at the median as well. The key difference here between these two applications is that because the packet size, the response size is fairly large, you would end up requiring multiple round trips to send out the message, due to which you see high latency, and then this exacerbates the latency, performance for the other baselines as well. Now I showed you how Krios outperforms the current existing orchestration stacks. Next, I'll show you how Krios is able to do that by simply augmenting different aspects on top of basic Kubernetes. So here, this is the latency profile for basic Kubernetes when it has one single application running in the constellation. And so in this case, we see that at first, the satellite is located far away from the region, so the latency is fairly high. As the satellite keeps coming closer, the latency keeps dropping till the point when the satellite is visible. You get the lowest latency at that time, and then the satellite keeps moving away, and the latency keeps rising, and this will keep repeating over time. So we've added the first component that I introduced for Krios, that is the mobility-aware scheduler, or the Krios scheduler. In this case, you can see that at the beginning, the satellite is directly visible, so you get the lowest latency, but because there is no notion of handovers, the satellite will keep moving away, resulting in the latency, which means that the latency keeps increasing. And then you get a similar structure like the previous one. Essentially, this is just like a shifted latency profile that you get here. Next, we added in a mobility-aware rescheduler. What this means is that at the point when the satellite is about to move out, the system will trigger a handover, will trigger an application handover, so that you have so that the application migrates to another node that is visible at that time. Now, while this outperforms the earlier two baselines by quite a margin, however, you can see that there are multiple of these latency spikes that you observe periodically. The reason for this is that when I say you need to perform an application handover, the application handover in itself takes in non-trivial amount of time. It's not that you say that like it's basically so it takes a non-trivial amount of time, because of which, since when you perform the handover right at the moment when the satellite is about to move out, you will see these latency spikes every time the handover happens. Therefore, to hide that, as I described earlier, you need to perform proactive, just ahead of time handovers, which is what Krios does, so that you hide the time, you hide the downtime that could have been observed at the time of performing the handover, so that you get the consistent low latency profile. Now, at the beginning of the talk, I had told you that deploying on the edge has two benefits. One is latency, which I just showed you, and then another is how many like the bandwidth savings. So here I'll briefly show you how all these cases stack compared to how many bytes you have on the different ground station satellite links involved here. So here you can see that in the first case, on an average, you will have around 20 kilobytes on the network, because you might have to go to reach a satellite that is fairly further away. Whereas Krios, because the satellite is always directly accessible, Krios can outperform like the baseline by 30x. So you're saving a lot on you're saving a lot of bytes on the network here. So finally, coming to to my final result, this is a key takeaway that I would like you to take from my talk, that Krios ensures availability with low overheads. Essentially, Krios is able to guarantee the same availability that 22 instances were able to do with on an average 1.03 instances. How this number comes is quite interesting. So most of the time, Krios will have a single instance running, but at the time of handovers, you will have two instances running. So averaged out, this gets you 1.03. This is the same graph that I had showed you earlier in the talk. Here I just added in the Krios number, and that is all you need. That is all you have. Like that is all you need to do. And secondly, Krios is able to achieve this with fairly low overheads as well. Like in this case, when I say that there are fewer instances running on the satellites, that means that you're using fewer resources on the satellites. But it's not just the satellites where resources get consumed. Like you will have the places where the orchestration stack is running, the network overhead. So we observe that even on the ground stations where we propose our orchestration stack to run, the overhead is fairly minimal, and the amount of bytes required to perform a handover are fairly low as well. And just to remind you, in the previous slide, I showed you the bandwidth gains that you can get with an edge. So these numbers, or this additional bytes, additional bandwidth usage because of handovers gets easily amortized by the bandwidth savings you achieve by successfully deploying an edge. So coming to towards the end of my presentation, I would like to say that working on this problem was a fairly fun ride, but during this time we found out that there are a lot more issues that come up here. So in this talk, I described to you what the design of an orchestration system for a LEO satellite edge should look like. However, we found that even determining where to run this orchestration stack is an interesting problem, because since the satellites are themselves ubiquitous and spread all over, you cannot have a single instance coordinating them. So you need multiple instances. And when you have these multiple instances, that brings in interesting questions about how do these instances coordinate with each other? How do you ensure consistency guarantees amongst those, and so on? In addition to this, we are also looking at adding energy awareness to the orchestration stack so that the orchestration system is aware about the energy budget of the satellites, and has a sense of the energy consumption profile for different applications. A slight variant of this work that I had been working on characterizing the route variability in satellite networks was recently accepted at PAM. This conference is happening next month, and I would encourage you all to join in and share your thoughts regarding the same. So finally, thank you. Thank you, Vaibhav and Mohammed, for providing this platform, and I thank the sponsors who have helped us fund this research. And I'll So yeah, feel free to reach out to me if you have any comments or you would like to collaborate. But now I think I can open the floor for questions.
Yes, that's great. Thank you very much for the interesting talks. So we have a couple of questions here. I will start first by the question from Topius. So he is asking about, instead of killing and reinitializing the service for a transition, have you considered container migration techniques? And if so, what is the overhead or the downtime with service killing and reinitialization?
So yes, I did not go into the details here, but essentially that is what we are doing. We have like an application instance is running as a container, so we have to migrate the container itself, and that is what I like. We observe that whenever a container migration would basically involve killing the instance killing the older container instance and deploying a newer one. So this task of deploying a new container instance takes a non-zero time. Like it can take a few hundred milliseconds to a few seconds, depending on the container runtime that you use, and that is why this downtime surfaces up that I was talking about in this slide. Yeah, that is how this particular latency spike or downtime surfaces there.
Yeah, that's great. We have another question from Peter. So what about routing? So I'm assuming that the satellite networking is tunnel based. So back to ground ground station, possibly not using IP technology for tunnels. But if you're deploying an apps on the satellite, so how routing would work? So routing must work as a flat, including satellites. Is that right?
Yes, you're right. I mean, I intentionally tried to sidestep that part as part of this talk because we look at that as a slightly different problem. Whereas, so first thing is ensuring that an application is always running on a satellite that is visible. And then we look at this as one of the next problems, as in being able to connect to the instance that is running that application. But yeah, that is a good question, and we have thought about that, but yeah, we consider that as a slightly separate problem here.
Yeah, I think there's also one interesting comment from Nitinder over the chat. So talking about the multi-instance orchestration. So he pointing to some link, so maybe you can take a look at it. Okay, so if there's no any further questions, so let's thank the speaker again.